This video will show a workflow using the gas AOF TPC analysis method for IHS VirtuWell, part of the IHS Harmony environment. The gas AOF TPC tool is primarily intended to be used for nodal analysis. Nodal analysis is a process that combines reservoir engineering with production engineering. Commonly, the node used is at the sand face, so the reservoir model describes flow from the extremities of the reservoir to the bottom hole, while the production model describes flow from bottom hole to surface. Since the reservoir model is independent from the wellbore production model, the goal is to find the combination of rate and flowing pressure that holds true for both the reservoir and production models at the same time. In IHS VirtuWell, the reservoir models for gas wells are the simplified model, also known as the back pressure or Rowland-Shellhart equation, or the Forkheimer model, also known as the LIT equation. Both methods work best with wells that have reached boundary-dominated flow, although the LIT method does have some applications for transient reservoirs. To start with, we are going to follow a basic workflow for nodal analysis using a simplified deliverability curve. This is also known as the back pressure equation or the Rowland-Shellhart equation. The easiest way to create an AOF curve is to have data available from a well test. However, when well test data is not available, then there are ways to estimate the AOF using production data. This video will show you how to build an AOF curve from well test data, but later videos will describe ways to build a curve using available production data. To analyze a well, find it in the Entity Viewer and then double-click it to enable the Analysis tab for that well. We will continue to use the condensate fluid properties from the previous videos. The available wellbores will be the same as well, with the initial wellbore consisting of only casing, with a second wellbore configuration that has tubing. To start an AOF TPC analysis, click on the thumbnail to create the worksheet. Then click the plus button to add an analysis method to the worksheet. We'll choose Gas Deliverability Simplified. The default calculation method is Use Sand Face AOF, which means that we're entering well test data. This method needs current average reservoir pressure, an N value, and either the AOF value or the Z value. Here are the values from our well test. With a reservoir pressure of 1000 psi, a sand face AOF of 2 million cubic feet per day, and an N value of 1. After entering the values, the deliverability curve is drawn. Commonly, the next step is to see where on this curve we are currently operating. To see that, we will build a tubing performance curve, sometimes called an outflow curve. A tubing performance curve, or TPC, starts with a fixed wellhead pressure in a wellbore and then describes what the sand face pressure will be for a range of rates. If there's only single phase flow, then we don't need any more information than that. But if there's multi-phase flow, then we should know the approximate ratios. The TPC we are going to build uses the following values. However, if you're unsure about what ratios to use, you can always look at your production history to try and find an average ratio from there. Here in Harmony, I've plotted CGR and WGR in the diagnostics plot to see what my approximate ratios should be. I'm going to use a ratio of 125 for my CGR and a ratio of about 1.2 for my WGR. Back in the AOF TPC worksheet, add a new analysis called Gas Tubing Performance Curve. Enter the wellhead pressure, condensate gas ratio, and water gas ratio, and finally select your wellbore and configuration. We're going to choose casing only since we want to see our current operating condition. Once the information has all been added, then a tubing performance curve is drawn. Of key importance is the intersection between the two lines, which is called the operating point. Hovering over the operating point with a mouse displays the intersection data. The red dot for an operating point indicates there is a probable liquid loading issue. This is also represented by the dotted line of the tubing performance curve. To see what would happen if we installed tubing into the wellbore, add a new TPC curve, use the defaults button to copy over the data from the previous curve, then change the wellbore configuration to tubing. Now we have two curves that we can compare. Because the operating point is blue, it indicates that liquid loading is avoided. In fact, we can see when liquid loading is likely to occur by following the solid line down to where it intersects with the dotted line. This indicates the combination of rate and pressure where liquid loading is likely to occur. We can do other comparisons as well. First of all, we can add another tubing performance curve, then copy the values over again. Now, if we wanted to see what would happen if we changed the diameter of the tubing from 2 7/8 to 2 3/8, all we need to do is customize the tubing, and then change the diameter to 2 3/8. In this case, our operating point has a lower rate, but we avoid liquid loading for a longer period of time. Therefore, the case is an economic choice. Another option is to see what effect compression would have on the system by lowering the wellhead pressure. If we uncheck the Customize button, then we revert to the flow path that exists in the wellbore editor. Then we can change the wellhead pressure, say from 210 psi absolute to 150 psi. This has the effect of both increasing our rate and extending the time that we will avoid liquid loading. However, it also comes at the cost of compression. So again, it is an economic choice.